This is part 2 on the lesson on galvanic cells. So in the last lesson, we looked at the zinc and copper galvanic cell. We have zinc at our anode, and zinc undergoes oxidation. It gives up 2 electrons. When the switch is closed, we have movement of electrons through the wire to the copper cathode, and the copper ions pick up 2 electrons and become solid copper. So we have reduction at our cathode, oxidation at our anode, and our electrons always travel from the anode to the cathode. And we can have a meter here, or we can have a light bulb or some other device where we use the chemical energy now that we have transferred it to electrical energy. All right, now I just want to go into a little bit more detail. Oh, and don't forget the salt bridge to maintain electrical neutrality. When our zinc puts more ions into the solution, when we put more positive charge in, we have to have our nitrate anions come in to neutralize it, so we have net neutrality in our compartment. And here we are losing positive copper ions as they become copper solid, so we need sodium ions to replace the positive charge there. All right, we're going to talk a little bit more about what is going on. Do these 2 electrons come off, travel through the wire, and come in? Not exactly. Okay, so we're going to go back to metallic bonding. So in metallic bonding, we consider the core of the atom, all the protons and all the inner electrons, and then our valence electron in the outermost occupied main energy level. And our theory of metallic bonding is that these valence electrons are delocalized, or they are mobile, that they can travel from atom to atom to atom. So we can think of it as musical chairs where everyone gets a chair. The music starts, this electron can come here, this electron there, this electron over there. So our valence electrons just willy-nilly go back and forth between different atoms. Now, when we have a wire, and this is the blown up part of the wire, and we have our anode and cathode, we know that our direction is going from the anode to the cathode. What happens is, if we have an electron that's traveling, that electron comes in, it pushes this electron over, pushes this electron over, pushes this electron over, pushes this electron out. So anytime an electron comes in, the electrons all jostle around and an electron comes out. So when we have those 2 electrons from the anode to the cathode, you can think of it as like all the electrons being in a line. So if 2 of the electrons come off of the line, everyone moves up 2, and then we have our 2 electrons come into the line. So just think of a line of people, 2 people in the front leave, everyone moves up, and 2 people can then come onto the back of the line. So that's how our electrons are transferred from the anode to the cathode. Okay, so we're going to do the mathematics of our galvanic cell, look at it quantitatively. And we need to define what is meant by this E, which stands for electromotive force. We could also abbreviate that as EMF. And the electromotive force is the driving force of those electrons through the wire. So we can think of it as the back electrons are pushing on the front electrons as they go through the wire, or we can think of it as the pull of electrons through the wire. The cathode is pulling the electrons, or the anode is pushing electrons. So we know that if we see the reaction happen, our delta G is less than 0 and it is spontaneous, and that spontaneity is resulting from this driving force, this E, that is pushing or pulling these electrons through the wire to get from the anode to the cathode. our E is measured in volts. And that is represented by a capital V. 1 volt equals 1 joule per coulomb. So a volt is energy per charge. So energy is in joules. Our charge we're going to measure in coulombs. So the coulomb, this is our SI, that's our official unit system. So this is the SI unit of charge. And we represent charge by a lowercase q, not to be confused with the thermodynamic Q. This is charge Q, lowercase q. So the electron charge, which we think of as -1, is equal to negative 1.602 times 10 to the negative 19th coulombs, which we can abbreviate with the lowercase c. And our proton charge in units of coulombs is positive 1.609 times 10 to the negative 19th coulombs. So one electron has a small unit of charge. So like I said, we've just been talking about electrons as -1 and protons as +1. This is just a relative charge in SI units. This is what we have. So we've done Coulomb's law before, and in Coulomb's law, our formula is F equals K Q1 Q2 over R squared. This Q is the charge in coulombs. So if we want to know the force between a proton and an electron, we would use these values for our Q. Q of the electron and Q of the proton. So Coulomb's law, the unit is the coulomb. Now, when we have our galvanic cell, the E0 of the cell, the electromotive force of the cell, is equal to the E0 of the reduction plus the E0 of the oxidation. So just like we can break our overall reaction down into half reactions, the electromotive force of the entire cell is equal to the reduction and the oxidation. So we want to calculate the E0 for our zinc copper cell, but first we have to look at how we're going to get these values. And what we're going to do is consult a reduction potential chart. Okay, so you should have printed that out, or you can look at your textbook. So here is a standard reduction potential chart. So that would be the E0 of the reduction, 25 degrees C. So standard means that our solution concentrations are 1 molar. And the way this chart is organized is that we go from the highest E0, the most potential, to the lowest, and that it goes into negative numbers. So up here, this is the greatest tendency to be reduced, and then it goes down. So we go from the greatest tendency to be reduced at the top, and then we go down at the bottom to the least tendency to be reduced. And as we go down this chart, we can see right here we have 0. So when hydrogen ions are reduced to hydrogen gas, that potential has been designated as 0, and everything else is relative to that. So anything above hydrogen has a greater tendency to reduce than the hydrogen ion. Everything below has a lesser tendency to be reduced than the hydrogen ion. Now, if we were to take one of these equations and flip it, we would have the oxidation reaction, and the sign of E0 would be flipped. So, our equation for the E0 of the cell, we need both the reduction potential and the oxidation potential, but typically you're only given reduction potential values because you're expected to be able to flip the equation and change the sign for the oxidation half reaction. All right, so let's use this chart to calculate the E0 for our zinc copper cell. So just to review, the overall equation for the cell is here. We have our oxidation half reaction, where the zinc gets oxidized to zinc ions, and then we have our reduction half reaction, where the copper ions get reduced to copper solid. The E0 for the cell is the E0 of the reduction plus the E0 of the oxidation. All right, so the reduction is the copper ion. So we go to our chart and we find that half reaction. The Cu, here it is, Cu2 plus 2 electrons goes to Cu solid, and our E0 value is positive 0.34. Okay, so this value is 0.34 volts, I wrote V, so 0.34 volts. Plus, now we need the E0 for the oxidation. The oxidation is the zinc solid going to zinc ions. So we find zinc on our chart, and zinc is right here. We need the oxidation. We need to flip this. When we flip this, then we get Zn solid goes to Zn2 plus 2 electrons. And our E0, we have to flip the sign since we flipped the equation. So our E0 then is positive 0.76. So you're always going to be flipping the oxidation sign. Okay, so this is positive 0.76 volts. So the E0 of our cell is 1.10 volts. And that is the same thing as 1.10 joules per coulomb, the energy per unit charge. So the higher this value, the more oomph or driving force the electrons have to go through the wire. Okay. Now, our reaction happens. It's spontaneous. So our delta G for our cell is going to be a negative value if the cell is operating. And here is our equation. Delta G0 equals minus NF E0. All right, so let's break this down. So N, this is the number of electrons transferred in the balanced equation in moles. Okay, this fancy F, this is Faraday's constant. Okay, named after Michael Faraday. And he was an English chemist from, he was born in 1791, lived till 1867. He has been called the greatest experimental scientist of the 19th century. He invented the electric motor and many contributions to the fields of electricity and magnetism. So you study physics, electricity, and magnetism, you will be hearing the name of Faraday. He also discovered and named benzene. So how about that? He had a dream of snakes going tail to head and figured out that's how benzene had to be in a ring. So anyway, that's his constant. So Faraday's constant, this is the magnitude of the number of coulombs per mole of electron. So we're going to calculate what that is. This is the magnitude of the number of coulombs per mole of electrons. So we know that each electron has a charge of negative 1.609, negative 1.602 times 10 to the negative 19th coulombs. We're just interested in the magnitude, so that means we don't worry about the sign. Okay, so we're going to calculate what Faraday's constant is. So x coulombs equals 1 mole of electrons. Okay, and we know how many electrons are in a mole of electrons. That's just Avogadro's number. So in 1 mole of electrons, we have 6.022 times 10 to the 23rd electrons. So moles of electrons cancel out. And then the charge, the magnitude of the charge, is 1.602 times 10 to the negative 19th coulombs for every 1 electron. So electron cancels electron. And a lot of times you'll see this with 3 sig figs. So I know that's 4 and 4, but we'll just use 3. So we get 96,500 coulombs. And we can write that as a conversion factor for every 1 mole of electrons. So that's the charge we get when we have a mole of electrons that travels through the wire. So that is Faraday's constant right there. And then the E0, that's just the electromotive force that we have just calculated. So now let's calculate the delta G for our zinc copper cell. So our delta G0 equals the number of moles of electrons transferred is 2. So we have 2 moles of electrons times Faraday's constant, 96,500 coulombs for every 1 mole of electrons, times our E0. We had 1.10 volts, but we're going to write it as joules per coulomb so that we can cancel out, do the math, and let's see what we get. So 2 times 96500 times 1.1 equals, I'm going to put that in kilojoules divided by 1,000. So we get 212 kilojoules per mole of reaction. Negative. Delta G0 is minus NFE, Of course, we have to have a negative delta G because that reaction is spontaneous. All right, so now we're going to do an example. We're going to do the whole thing. So we're going to draw an aluminum cadmium galvanic cell, calculate the E0 of the cell, we'll write the overall reaction, and then we'll calculate the delta G0 for the cell. All right, so we're going to draw our cell. So we're going to make our 2 compartments. Now, I always have a tendency to put the anode on the left, but it doesn't matter. If you had these beakers on a table, you could just walk around the other side of the table, and then they'd be on opposite sides. So it doesn't matter which compartment you put left and right. All right, so we're going to have a piece of our metals. So I'm just going to make this cadmium, and this is going to be aluminum. And we're going to have our wire, and this time we'll put a voltmeter. Sometimes you'll see that. That measures our EMF. And we need a solution. And we're going to do standard state. So in here we'll put 1 molar cadmium nitrate, cadmium 2+. And in here we'll put 1 molar aluminum nitrate, NO3, 3. So in here we've got CD2+ ions, and in here we have Al3+ ions. So now we need to figure out which one of these is the cathode, which one of these is the anode. So we're going to consult our chart. So we want to see which of these has the greater reduction potential. So remember, our chart goes from greatest reduction potential to lowest reduction potential. So we look for cadmium and aluminum ions and see which one has the higher value. So start at the top. Oh, here we go. Here's cadmium. Right here. And then let's look for, and then here's aluminum down here. So the cadmium has the higher reduction potential. Even though they're both negative, this one is a less negative value. So this is a higher reduction potential. This means that the cadmium is going to be reduced, and that is our cathode. So this then, with the cadmium, is our cathode, where we have reduction. So the aluminum must be the anode, where we have oxidation. And our electrons always go from the anode to the cathode. So we have electrons leaving and electrons coming in. And then we have our salt bridge. Let's say we got to put potassium. We'll put potassium perchlorate in here now. That'll be on our salt bridge so that we can maintain electrical neutrality in our cell. Okay, so let's write our half reactions and get our E0s. So this, we said, is the reduction. So our reduction half reaction is the CD2+ ions take 2 electrons and become solid CD. Remember, Leo says GER, reduction is gain electrons. In our other compartment, our anode, where we have the oxidation, this is where our aluminum metal loses electrons and becomes Al3+ plus 3 electrons. Now the E0 for our reduction, get that from our chart, and our chart is reduction potentials. So there's our equation, just like we wrote it, and we have negative 0.40. And this is negative 0.40. Now we want the E0 for the oxidation. So to get the oxidation, we have to reverse the equation and reverse the sign. When we reverse the equation, we get Al going to Al3+ plus 3 electrons. So our E0 of oxidation is positive 1.66. Reverse the reaction, reverse the sign. So this is positive 1.66. I forgot my unit. Volts. So now we can get the E0 for the cell. So the E0 for the cell equals the E0 of the reduction, negative 0.40 volts, plus the E0 of the oxidation, 1.66 volts. So we get a value of positive 1.26 volts. Okay, what we're going to do now is write the overall reaction for the cell. And I'll do this up here. So if we have CD 2 plus 2 electrons goes to CD, and then we have AL goes to AL3 plus 3 electrons, and we want to be able to add these up. We have to be able to cancel out the electrons. So if we multiply this by 3, we get 3, 6, and 3. Multiply this by 2, we get 2, 2, and 6. So now when we add, our electrons cancel out. So we get 3 CD 2 plus 2 AL yields 3 CD plus 2 AL 3 plus. So aqueous, solid, solid, aqueous. There's our overall reaction. So now we're going to calculate the delta G0. So delta G0 equals minus NFE0. Minus, didn't forget the minus sign this time. Okay, what is N? N is the number of electrons that got transferred. It's the 6. It's the number of electrons that cancel out when you were getting your overall equation. So minus 6 moles of electrons times 96,500 coulombs per mole of electrons times 1.26 joules per coulomb. And let's figure out what that is. So negative 6 times 96500 times 1.26 equals, divided by 1,000 for kilojoules. So we get negative 730 decimal point kilojoules per mole of the reaction. Negative, oh my God, our delta G0 is negative. All right, so that's it for today.